of the moon, Mars, and asteroids. She's a very busy person. She's part of the science teams for the Curiosity and the Perseverance rovers on Mars. She's also the PI for the mass spec on the astrobiotic Peregrine lunar lander. She also leads the science team for the Lunar Flashlight mission, which will be aboard Artemis 1, and serves as co-chair for the Artemis 3 science team. So we are super excited to have her. She's going to tell us a little bit about exploring the moon on the Artemis path. Thank you.
Thanks, Jamie. Thanks for having me, everyone. Clive is a real hard act to follow, but I'm really, really glad that he set up the science of the moon and the evolution of the moon and what we learned from Apollo. And where I'm going to take you is what we're going to be doing in the next several years, particularly in the robotic arena. So I haven't been around as long, but I know that I shouldn't prognosticate what NASA's going to do more than maybe 5 years in advance. So we'll just stick to what's coming up. Oh, okay. We're bringing that presentation up. Okay, so probably many of you have heard about the Artemis program. The Artemis program is NASA's return to the moon, or going forward to the moon, as we like to call it. And this is going to use the SLS rocket, the Space Launch System. It's just this much bigger than the Saturn V, so that we can do things bigger and better. And that's going to be coming up in 2024 or shortly thereafter. But before you put humans on your big giant rocket and launch them, you want to make sure to test that rocket, make sure that everything's working really well. So we're going to have 2 or more test flights before then that are going to go to the vicinity of the moon. When we talk about going to the vicinity of the moon, that gets us out of low Earth orbit, it gets us out of the gravity well of the Earth and enables us to have things that ride along that are going to go to the moon, that maybe are going to orbit the moon or land on the moon or fly by the moon. And so those are the kinds of things that we're going to be doing in the next several years. So what I'm going to talk about is things that are riding along on SLS-1, which is going to launch pretty soon, hopefully the beginning of next year. There are some CubeSats that are going to be launching there. We're going to have commercial landers. You heard Dr. Zurbuchen earlier talk about public-private partnerships and commercial opportunities. So I'll tell you a little bit about those, and then you're going to hear Tony Colaprete after me talk about the Viper rover, so you'll get into even some more detail. Fantastic, thanks. Okay, yeah, so here's Artemis phase 1 to the lunar surface. This is what's going to get us to that kind of sustainable presence on the moon. It's going to be the first stage of building up the base camp on the moon. This is going to be like an Antarctic outpost, where we have mostly researchers that are populating that, but we hope to have it sort of continuously operated either by humans there or teleoperation, and that enables us to do long duration experiments, some of those for geology and the atmosphere of the moon, the tenuous lunar atmosphere. I'm sure this is going to be of wide interest to more people than just lunar scientists. Obviously our biologists are going to be interested in that kind of long duration. But before we get there, we've got this whole path coming up, and I'm going to focus really down here on the lower left, like I said in the very beginning. So commercial lunar payload services and early South Pole missions on Artemis 1. Okay, so Clive gave you this great introduction to what we know about the moon, primarily through the Apollo missions that returned samples to us and did a lot of the field geology and the field relationships. So the moon itself doesn't have the extremes that the Earth does as a planet, right? So as he said, we don't have plate tectonics, we don't have oceans, things like that. But the moon is totally a planet, right? It's got a crust, a mantle, and a core. It's got volcanism that extrudes material out onto the surface. It's got impacts coming in. So it behaves very much like a planet. It is, in fact, from those samples that we learned how all planets behave, even the Earth. So the changes on the moon or the variations on the moon are more subtle than they are on the Earth, but they are very, very valuable for understanding how planets form and evolve. We apply this knowledge to the Earth, to Mars, to all the planets to see how they differentiate, how they lose heat, how their plates form and thicken, and what that material does over time as impacts in the solar wind impinge on it. So we're going to the South Pole with Artemis. The South Pole is a special place on the moon, and on the Earth too, of course, or any planet where it's inclined just slightly to the plane of the ecliptic. And what that means is the sun is, pointing to the equator, and the less inclined you are, the more that your poles only see slantwise sun angles, right? So as the sun goes around the horizon, it never goes directly overhead. That's fine if you're on a flat plane like the Antarctic Peninsula, you can see the sun above the horizon. But in the wintertime, if you live in the city, you know that if you're, among big buildings, there are places where the sun doesn't go overhead and those ice patches persist for a long time. It's the same at the moon, at the poles of the moon. The sun goes around the horizon and never goes into some of those craters, and they're very, very cold. They're 35 Kelvin. That's the temperature of the surface of Pluto, and it's literally in our backyard. So we have a real opportunity to find things that get collected in very cold places like volatiles and really start to understand the role of volatiles on the moon in a way that we could not do for Apollo. We hadn't even formulated those questions during Apollo. This is our first real chance to work on these kinds of questions about the volatile cycle of the moon, how volatiles accumulate to the moon, where they go after they accumulate there, and whether those are really resources. So a resource means something that you can use maybe not once, but multiple times, right? Otherwise, it's a very limited resource. If we don't have water accumulating to the moon all the time, we might be able to use it once, but we're not going to be able to use it again. So we need to really understand that. As we talked about, the sun impinges directly, the solar wind impinges directly on the lunar surface. So if you have hydrogen screaming in and you've got oxygen-rich rock sitting on the surface, you can create volatiles that way. It also drives the tenuous lunar atmosphere, or the exosphere. So that's something that we want to learn more about. That's something that space weather has a lot to do with, and keeping our astronauts safe. Not only are astronauts safe on the moon, but keeping all of our assets around the Earth safe, and making sure that all of our GPS and phones and everything that uses those satellites are here to serve us. I'm not going to talk too much about the impact history of the Earth-Moon system. Clive talked a little bit about it. That's one of my areas of interest. But that is something that we need to know more about, because there is a time in the moon that we think was the late heavy bombardment, or the terminal lunar cataclysm. It's a time about 4 billion years ago. That is also the time of our least common ancestor on the Earth. That least common ancestor was a hypothermophile, as far as we know now. Is that because they survived this late heavy bombardment and came out on the other side victorious? Or is it because they evolved in that very energy-rich environment of late heavy bombardment? Or is it totally unrelated? It could be completely coincidental. We don't know, but that's in textbooks now. There's some evidence on the moon that that may not be the case anymore, so we really need to figure that out. We can put platforms there to study the universe, and we can study all planetary processes. So there's a lot going on at the poles of the moon. This is a video. I'm not sure whether the sound's going to play, so if the sound doesn't play, I will just narrate it for you. This is about the secondary payloads on the Artemis 1 rocket. It doesn't sound like the sound's playing. So here's an animation of the SLS taking off. This is going to be an amazing launch. I wish that I would get to go see it. Maybe I'll get an invitation. So the SLS is taking off, this very, very powerful rocket. On top of the SLS is the Orion spacecraft, which is the crew spacecraft. On the first launch here on Artemis 1, it is uncrewed. It's to make sure that the crew would be able to survive. It's going to be fully instrumented, taking all those measurements that you need to apply to humans. It's going to separate, obviously, from the booster, and so now it's being propelled by the upper stage up past low Earth orbit, and it's going to get propelled into a figurator on the moon, a distant orbit around the moon. So as that's happening, you've got an adapter ring. So there's the Orion separating, and you've got an adapter ring that's now gotten left behind from that upper stage. So we're going to focus in on that adapter ring. There it is. So as that's falling away, it's just sort of in free space right now. Inside that adapter ring are the payloads, or the CubeSat payloads. There's 13 spaces for them. There they are. So these are 6U CubeSats. There was a wide call over many disciplines for 6U CubeSats that could fit into this kind of system. It's brand new. It's a new opportunity, and all of these are in free space, like I said, so they can use in-space propulsion, which is something that's new to us and that NASA really wants to develop. So they get pinged off in free space. They're going to open up their solar panels, get their power, detumble, turn on whatever propulsion system they need to do, and then they're going to go and do their missions. Some of them are going to the moon. They're going to propel themselves to the moon. Some of them are going elsewhere, like near-Earth asteroids. Some of them are just going into free space to do their kind of free space experiments. So there you see the little spacecraft running away. So I want to talk about or highlight the lunar payloads, just because that's what I was asked to do. So there's 4 or 5 different payloads going to, or satellites, full satellites going to the moon, and they're going to do either flybys or lunar orbit. So LunaMap there on the bottom left is going to be a neutron detector that detects water in sort of the upper meter of the lunar regolith. This kind of experiment flew on both Lunar Prospector and the Lunar Reconnaissance Orbiter, but from a pretty high altitude. That means the footprint is pretty big. This is going to take very close passes over the South Pole and attempt to localize that deep water. Lunar Ice Cube has a visible light near-infrared spectrometer that's going to give us the signal of water ice. This is kind of like the Moon Mineralogy Mapper, but it didn't go out quite far enough into the infrared to capture the water signal. So Lunar Ice Cube is going to be doing that at the equators. So that's going to be looking at the diurnal and seasonal variability in the water signature at the equatorial latitudes. Lunar is a commercial payload, and it's going to fly by the moon and take some data that Lockheed Martin's going to want to use for future missions. We have international payloads. Omotenashi is a Japanese payload that's got 2 little mini landers on little mini airbags. It's not a rock on the front, that's a little mini airbag. And they're going to drop them onto the moon and attempt to have tiny little instruments actually land on the moon. There's a lot going on these, but I want to give 2 honorable mentions that aren't on this slide. Lunar Flashlight, which is the satellite that I'm the measurement lead of, did not make its Artemis integration in time, so we will not be flying on the Artemis rocket the way we originally wanted to. We're going to be looking for another rideshare, and that is going to be using active laser spectroscopy to look for surface correlated water ice. Now the Luna H map looking for that deep water ice, we're going to be looking at surface water ice, and fun fact, they are not correlated on the moon. They don't seem to be talking to each other as reservoirs. That kind of means that they may have been put there by 2 different processes. That means they may have different evolutionary paths or they're different ages. We don't quite know yet. That's a place where we need a lot more information to understand whether we can use that water as a resource. And the other thing I'll just mention too is a satellite called BioSentinel, which is just going into free space. It's got some genetically engineered yeast strains on it and a microfluidics experiment to rehydrate those strains at different times during the experiment to understand how often DNA breaks occur in those strains of yeast. They've also got an equivalent experiment on ISS and one at Brookhaven National Labs. So we're going to be able to understand the effect of radiation across the whole radiation spectrum in space and its effect directly on biological organisms. Commercial lunar payload services, and this is something Thomas talked about, is our public-private partnerships with commercial companies. So this isn't quite buying data from companies that are already doing this, but there's a lot of companies that want to put your payload on the moon. They're begging for your business. Now you have to sort of raise the money to make your payload and to pay them to put it on the moon, but there are plenty of opportunities. All of these companies, they're online. A lot of them have payload user guides. If you can bring the experiment, they would love to fly it for you. One of the interesting things about commercial lunar payload services is that these are new companies. They're trying things as sort of this generation's answer to putting putting landers on the moon. We haven't had that great of a track record in the last couple of years about landing things successfully and safely on the lunar surface. It's actually really difficult. We don't have an atmosphere to slow us down with parachutes the way we do when we land on Mars. We have to use solid rocket motors to brake return and land softly on the moon. Then there's a lot of thermal challenges on the moon. The moon goes from very, very hot to very, very cold very quickly. So it's actually pretty challenging to land there. There's a lot of companies that want to do this. We hope that we're a part of it. We are really glad to have a lot of different payloads on these that are going to be doing some science and some like real integrated decadal level science, which is very exciting, all over the moon. So these are coming up opportunities twice a year. Is what we're hoping to do. 2 launches a year, 2 landings a year, 2 landing attempts a year. And you can see that about half of them are going to more or less equatorial regions on the moon, more or less places that we have scientific interest in. And a whole bunch of about half of them are going to the South Pole itself. And we're going to learn more about what we might want to do with humans when we go to the South Pole. This is totally an incomplete payload list, but it's like, how many more can I fit on a slide? There's like 24, there's more than 24 payloads flying now, just from NASA and lunar science. So there's technology development missions from STMD, there's human relevant instruments from HEO, there's science instruments, there's just a whole bunch of really great experiments going up. One thing that's kind of scary about working in the CLIPS realm, and this is mine, this one, PITMS is mine, and I'm really excited to be flying it. But one of the things that's kind of scary about it is the landing folks, the people who are building the lander, they want to build it, they want to try it, and they're okay if it fails because they're going to get to do it again, right? The people who are managing these instruments and building these instruments, they're like, yeah, let's try it. Let's get out there, let's do this. The scientists are like, where's my paper? So I don't get my paper about the results until it lands successfully and returns a successful science. So this is something that we're still kind of working out, is what is the risk to the different stakeholders in this kind of scheme? And what is the risk to scientists? If your experiment doesn't work, did you not write papers for 3 years and hoped for this to work? So we've got to get a little bit better about our risk to scientists. But right now, it's a really exciting place to be working. I'm not going to talk about Viper. Tony's going to talk about Viper. Viper is going to be our rover on the moon that's going to be looking specifically for in situ resource utilization. It's had a long and storied history, and we're really glad that it's going to be flying. And it has dual use for science as well. Science and exploration go hand in hand. If we want to learn about where these volatiles came from and whether we can use them, we need to know the science of it. When we're talking about exploration geology, we didn't go out to California and just sink a well every kilometer and hope there's gold. You do the geology of it to figure out what concentrates the elements, and then you go find the geologic places that have those conditions that allow you to find the elements that you want. That's what Viper is going to be doing for us. And Lunar Trailblazer is a small mission, not as small as the 6U spacecraft, but small, and it's got 2 instruments on it that are going to be looking more at the spectroscopy of the lunar surface to follow up on some previous missions that maybe didn't do everything that we wanted to do. The exciting thing about working with these small spacecraft, and this is run out of Caltech and JPL, the exciting thing about working with these small spacecraft is the ability for us to bring new people in with new ideas, get them rapidly to the moon. You heard Thomas talk about this. The challenge is that small spacecraft have to do everything that big spacecraft do for planetary missions. Even as far away as the moon, we can't just use UHF signals the way we do in low Earth orbit. We can't orient ourselves using the magnetic field of the Earth. We have to use active attitude control systems. That means propulsion, expendable resources. We have to actually get to places. Even though we get dropped off in free space, we have to use active propulsion to go to the moon. To get into a polar orbit the way that Lunar Flashlight does, we have to make a plane change that requires some delta V expenditure. That means bringing a propulsion system with us. So cramming all of that into a little spacecraft is very challenging, but even if they work, that's awesome. Even if they don't work, we're miniaturizing those technologies. They're going to be available widely for other people to use on different kinds of missions or even bigger missions. If you use a bigger mission with smaller parts, you got more room for payload. So a lot of the technologies that we're developing for these, the science is going to be great, the technology is going to be, we're really excited. So 2021-ish now means 2022-ish. So look for that coming up next year, the Artemis 1 mission. It's going to be exciting to watch a giant rocket, go from lunar soil and be a precursor for bringing humans to the moon. It's also going to carry these CubeSats, which is going to be a fun and interesting experiment. CLIPS missions coming up, that one 2021 is also ish. I think the first one's going to be in early 2022 now, but 2 a year, that's astonishing to have things on the moon. We're going to be eyes on the moon twice a year and beyond. More robotic missions, Trailblazer, Viper, there's a capstone mission coming up, which is testing the near rectilinear halo orbit that the Gateway will go into. So there's a lot of robotic missions coming up that are going to give us eyes on the moon, that are going to turn our attention there. And with those opportunities come times that we can expand our community and we can bring more people in. And that's what we really want to do. So we're going to have tons of workshops. We're going to have tons of science opportunities. Please, please, please attend those. We want your voices. We want everyone's voices to be heard in crafting that program. So as we move toward Artemis Base Camp, I hope that you will come along with us. Thanks.
That was so wonderful. We have questions too at 855-855-1413.
So a tote bag when you.
I know. My best, my voice here is cracking here. But do you anticipate sample return? So what is sample return? Is it only going to be regolith, or are there biological samples that might have a chance to come back?
Yeah, good question. We want all the samples. So Kevin Sato is here, and he's working VPS at NASA. That's my counterpart. We're bringing back all the samples. We're a little bit limited in our early missions by what Orion can physically hold inside that crew capsule and bring back to the Earth. But if some of these robotic missions work, those robotic missions can also do sample return, either collected by crew and launched back on a robot, or the robot itself can do sample return. We do want that capability because we want them from a variety of different places on the moon, not just where human crew go. But the Artemis 3 Science Definition Team Report is out, and you're welcome to go read that. And we recommend a huge suite of geologic samples, regolith, rocks, volatiles, core samples, things that are sealed so that we can seal those volatiles inside. So yeah, a whole variety of things.
Maybe this is going to be a question for Tony, but what missions that will drill into the moon?
Yeah, well, Viper will for sure, but there are also a couple CLIPS missions that are bringing drills as well. So the drill that's flying on Viper is also flying to a South Pole landed mission, that Trident drill. And then there is another one that's a European payload that's got its own drill, and those are intended to bring volatiles up from the subsurface and analyze them with onboard payloads. It's a very similar model to what we've been using on Mars for more than a decade, very successfully. I work in the Mars program as well, and it's a wildly successful program for both observing the planet and getting really detailed analyses with our detailed instruments. That's where we want to go. We want that for the moon too.
So this is a question, what kind of structural health monitoring is involved in the Artemis 1 mission?
I don't know. I don't know the answer to that. Sorry. I can help you find that. If you find me afterwards, I can help you track that down.
Another question is, what experiments are being planned for the Artemis 3 mission, which will it have direct human involvement?
So some of them will and some of them won't. The Apollo missions had what they called suitcase science that were deployed by astronauts. So, similar to some of the things on the ISS where it's semi-automated but some human interaction. I think those are going to be available if you need to unpack or set up your experiment. I think there'll be opportunities for, just like these CLIPS landers, for fully automated experiments to go. Those are intended to be competed opportunities. So you're going to need to look out for AOs from NASA for competed opportunities to send payloads to the surface. So they are intended to be there as an opportunity for the community, but it's going to be your creativity that drives those.
So questions are pouring in here, but what are your concerns about contamination, planetary protection? How are they going to be addressed on the moon?
Planetary protection is something that we're always considering. As Clive said, there are no moon bugs, but planetary protection is still something that's in effect for the moon, and we do have to take specific precautions. They're not as stringent as for other places that may harbor current life. But one of the great things about the moon is that it's a blank. It's a life detection blank. So all of the things that Clive said were coming in, there's organic material coming in, there's processes that are happening on the moon with UV radiation breaking things up and reforming molecules. That's a life detection blank. When you send your instruments there, that's what you would see as the background with no life, so that when we go to Europa or we go to Mars, we have a level that we know should be there from normal geologic processes. So we don't want to mess that up. We do have planetary protection for that, but astronauts are dirty. People are dirty. They're going to be exhaling. They're going to be leaving waste behind. There's already waste left behind.
As a microbiologist, I resent that remark.
You can't sterilize a person the way you can spaceflight hardware. So that is something that people absolutely are looking at in the context of planetary protection. But we've been to the moon before, so if you think we're going to mess it up, we've already messed it up.
So what happens to all of the SLL rocket components that get detached in space? Are there any way of Artemis recovering that space debris?
No, almost all of it is expendable. The Orion will come back, but the launch abort system that comes off and the rocket itself and all of those boosters burn up in the atmosphere.
So how is the dust challenge going to be taken care of on the moon to conduct experiments?
I don't know. I know there are people who are actively working on this. We've known dust is an issue. I won't necessarily say it's a problem because it's something that you can solve through clever engineering. So that just means it's an issue that you need to address. So people are definitely working on addressing that. Clive showed you some great pictures of the lunar soil. Not only is it small, it's abrasive, it's jagged. The good thing is that unlike Mars dust, it doesn't appear to be chemically reactive. Mars dust is chemically reactive as well. So people are looking at judicious use of filters. People are definitely looking at piezos or electrostatic repulsion. They're looking at things like just leaving the spacesuit out in an airlock. You see that a lot in sci-fi movies, but it's very effective. Just leave it outside and don't take your dust inside. So there's a lot of different things that you can do in the architecture that people are exploring.
So building on the planetary protection comment earlier, it's also about non-biological contamination, like protecting volatiles from particulates from fuel. So are there any measures to protect your samples?
Yeah, so the great thing about solid samples of the kind that we're talking about for geology is that contamination is in the eye of the beholder. Just because you're adding something to a sample doesn't make it contamination. If you can figure out what it is and effectively see through it, you don't even have to remove it. You can just be like, oh, I see a signal in my mass spec from the fuel. I'm going to ignore that. So as long as it doesn't react or cause interference with what you're looking for, it's not really a contaminant. So yes, we are looking at those things. We have looked at them in Apollo. There's a couple great papers looking for the fuel from the Apollo lander in the samples that were picked up right below the lunar lander, and there's no sign of fuel in those. So it's possible or probable that some of those molecules do get absorbed and then ping back off, but you've got a pretty complex landing plume where stuff is being jetted away as well. And even if that does happen, even if they do get adsorbed onto the surface, we can break the rock open and look at the inside where things didn't get in. So yeah, we pay attention to that, but I don't think that it's a problem in any big sense.
Okay, so for the last question, I'm going to focus on the students. So I'm going to merge a couple questions here. So this is really exciting time for students to get involved. And what science are you excited for students to get actively involved in the next decade? And how would you recommend students become more involved in the ongoing payload projects?
Yeah, that's a good question. Personally, I always say that you should do what you love, because if you're a student and you're working on something that you don't love, you're not going to be a student much longer. You're not going to be a very good student. So if it doesn't thrill you, find something that thrills you. The space program in NASA, largely, we need all kinds So yeah, I'm a lunar scientist. We've got biological scientists here, physics, all of the disciplines. Every science discipline that you can imagine is well represented at NASA. And NASA is not just civil servants. In fact, NASA is few civil servants. NASA is mostly giving grants to universities and soft money institutions for those people to do science as well. So you're part of the NASA family, no matter where you're working. But we also have lawyers. We have space lawyers. We have procurement people. We have artists. We have storytellers. We have all of those people are part of the NASA family, and they're all really important to getting us to go to the moon. So what I would say is find what you love to do and stick with it and get really good at it. And then find the people at conferences like this. Go to conferences, find your advisor and say, I really want to be involved with this. Do you have any colleagues who we could talk to? Get your networking done. It's maybe not the most merit-based system that we would like it to be, but it is effective.
Well, thank you, Dr. Cohen. That was an amazing talk, and appreciate it. So the last speaker of the President's Plenary is Dr. Tony Colapreti. He's a planetary scientist